Hello everybody and welcome back. In this presentation we are going to be talking about how to find the equation for a demand function without having to do the graphical process we looked at the last one. So in the last presentation we used graphs to figure out what a demand function might look like, and now we're actually going to do math and get at the end of the process a specific demand equation. So this process is going to be very, very similar to when we did finding an optimal bundle algebraically. It's going to be the same set of steps and a lot of the same math. So if you want to, you might want to go back and review that quickly, look at your notes or any kind of practice problems you did, because just to get re-familiar with it, because it's going to be basically the same thing. Okay, so same as we did before when we were finding optimal bundles algebraically, we're going to find the slope of budget constraint. We're going to use the power rule on a utility function in order to find the marginal rate of substitution. We're going to set those equal. We're going to do some substitution with the budget constraint, etc., etc. Okay, so here's the example. Assume that there are two goods, X and Y. Our goal is to find the demand function for good X. So in the end, what we want is an equation that is a function of the price of X. So we want the quantity of good X, and then the equation is going to be involving the price of X. Something involving PX. Okay, so our income is $600. The price of good Y is $25 per unit. So as usual, as I was saying at the end of the last presentation, these two numbers are going to be a constant in this process. When we are deriving a demand function, your income and the price of other goods, those are held constant. So in this case, our income is going to be $600 and the price of good Y is going to be $25. Okay, so since we wanted, so the difference now compared to when we were finding the optimal bundle algebraically before is that our final answer when we were finding an optimal bundle was exactly that. The answer was a bundle. It was two numbers. I'm going to consume this much of good X and I'm going to consume this much of good Y. The end product of this process is going to be an equation that involves the price of good X. So we want to be able to see how will my quantity demanded change as the price of good X changes. So in the previous work we did, we would have written our budget constraint filling in actual numbers for both prices, for both the price of good Y and the price of good X. Since we want to end up with an equation that involves the price of X, we're going to leave the price of X as a variable called PX. So our budget constraint is 25Y, because the price of good Y was $25, plus PX times X. So this term represents the amount of money we spend on good X. That has to be equal to $600. Okay, here's our utility function. Step one is to find the slope of the budget constraint. So I'm going to put up a play posit question. I'll let you give that a try. I'm going to write I think the answer is on the next slide. Okay, the slope of the budget constraint is just the price of the horizontal good divided by the price of the vertical good. In this case, PX is the price of the horizontal good and 25 is the price of the vertical good. So the slope of the budget constraint is just PX over 25. Okay, so now we are going to apply the power rule to our utility function. Now we're on step two. Our end goal is to find the marginal rate of substitution. Just check something real quick. Okay, so I'm going to do most of the work on this slide. I'm going to go step by step. So the first thing I want you to do is apply the power rule to the utility function, treating X as the variable. So I want you to find du dx, which is the marginal utility of good X. So go ahead and I'll put a play pause question asking you to put this in, and I'm going to pause it and write in the answer, and then we'll come back. Okay, so this is the marginal utility of x. When you apply the power rule to the utility function with respect to x, you bring down the exponent on x, which was 0.35. You subtract 1 from the exponent, that gives you negative 0.65, and then y to the 0.65. Since we're treating x as the variable, y is just a constant, so we leave it alone. Just doing a little simplification, moving the negative exponent to the denominator, you get 0.35y to the 0.65 over x to the 0.65. Okay, so now I want you to do the same thing. I want you to apply the power rule, this time treating y as the variable. And I'll pop up a play pause question for you to put in your answer, and I'll write mine up, and then we'll go from there. Okay, so here I applied the power rule to the utility function with respect to y. So we got the marginal utility of y. I brought down the exponent on the y, which was 0.65. That's where that came from. Subtract 1 from the exponent on y, you get negative 0.35. Again, we're treating y as a variable, so x to the 0.35 is just a constant. We leave it alone. So we get x to the 0.35. Simplifying, moving the negative exponent to the denominator, we get 0.65 x to the 0.35 over y to the 0.35. Okay, so now we need to find the marginal rate of substitution. So hopefully, as you recall, the marginal rate of substitution is just the ratio of the marginal utility of x divided by the marginal utility of y. So go ahead and try to work this out. You should get some nice simplifications. And I will pop up the answer in just a second. Okay, here is the work to get the marginal rate of substitution. So I just plugged in for marginal utility of x. So we got up there, over marginal utility of y, which is what we got previously. When you are dividing a fraction by a fraction, you multiply by the reciprocal. So marginal utility of x is right here, times the reciprocal of the marginal utility of y. 0.35 times y to the 0.65 times y to the 0.35. You have the same base here, so you just add the exponents. 0.65 plus 0.35 is just 1, so you get in the numerator 0.35y. Same deal in the denominator, you get 0.65x. And then I just divided 0.35 by 0.65. That gave me 0.5385 times y over x. So that's the marginal rate of substitution. All right. So we're getting closer. What we want to do next is to set the marginal rate of substitution equal to the slope of the budget constraint. So that's what I'm doing here. This was the marginal rate of substitution. This was the slope of the budget constraint. I just cross multiplied here, and I got to this. Okay, so that gives me an expression that I can plug into the budget constraint. So the next step was to substitute back into the budget constraint. So that's what I'm doing here. So here's the budget constraint. I moved the xpx to this side here, and then divided by 25. So I solve for y. So solve for y. And now I'm going to plug this back into this equation. I'm going to replace y with 600 minus xpx over 25. So this piece right here, that is what y is equal to. Okay, so to get to the last step, to solve for a demand function, we need to solve this guy for x. So you want to try to get x all together on one side. So that's an exercise in algebra. I want you to try it and put in what you think you get for the demand function. So your demand function should look like x equals, and then some stuff on this side that involves only numbers. and px. So there should not be any x's left on the right-hand side. So give it a shot, and the right answer will be on the next slide. Okay, so this is all the algebra to solve for x. This is where we left off on the previous slide, so that's just copied over. This step, I just divided 13.462 divided by 25. So I just simplified this. In the next step, I just distributed the 0.5385 to both the terms in here. Now I'm trying to move everything that has an x in it to the right-hand side. So this term has an x in it, so I want to move it over. So I added that to both sides. So now I have on the right-hand side 1x px plus 0.5385 x px. Those are like terms because they both have the same variables, x px. So you can just add them together. You get 1.5385 x px is equal to 323.077. To get x by itself, I need to divide both sides by 1.5385 px. So that's what I did. To simplify, finally, you just divide 323.077 by 1.5385. That's where this 210 came from, over px. So the demand function is x equals 210 over px. The graph of that function is over here on the left. This is what 210 over px looks like, where, whoops, it's quantity of x, and px is on the vertical. Notice that, so again, this is coming back to what we were talking about earlier about what's being held constant. In our final answer, this demand function, the only variable in it is the price of x. However, we did use the 600, that was our income, and 25 was the price of y, of good y. So our income and the price of other goods did impact the number we got in the numerator here. Those constants are contained inside of the value we got in the numerator. So even though the only variable that appears in this equation is px, changes, if we went back and had changed income to something else or changed the price of y to some other number, we would have gotten a different answer here. And in future presentations, we're going to talk about how changing those values would impact the demand function that we got at the end. Okay, so there's an example on the next page for you to go through the whole process. Okay, so I'm going to go step by step, find the slope of the budget constraint, do the marginal rate substitution. I'm going to pop up places for you to put it into PlayPosit. So first, let's find the slope of the budget constraint. I'm going to write it on the page. You put your answer in PlayPosit. Okay, the slope of the budget constraint should be px over 30. Next thing I want you to do is find the marginal utility of food. So we're moving on to where we need to find the marginal rate of substitution. So put into PlayPosit your marginal utility of food. Okay, here's the marginal utility of food. I applied the power rule, brought down the 0.8 in front, subtracted 1 from the exponent on f, left h alone, and then simplified the negative exponent. You get 0.8 h to the 0.2 over f to the 0.2. All right, now I want you to find the marginal utility of housing and put your guess into PlayPosit. Okay, here's the marginal utility of housing. You get 0.2 f to the 0.8 over h to the 0.8. Now I want you to go ahead and combine those into the marginal rate of substitution. Our horizontal good here is food. So we're going to put